Hello, my name is Catherine Beckett, and today I'm going to go over an interesting mathematics topic, Goldbachs Conjecture. More than that, I will be going into what would happen if, instead of addition that is used in the original conjecture, subtraction was used. I will go into detail of 3 cases that come from the subtraction application, an even integer case and 2 odd integer cases. But before delving into the manipulation of the math, I will briefly go over some notable things in the life of Goldbach and how he has inspired the subtraction alternative to his conjecture. Christian Goldbach was born in 1690 in Königsberg, Prussia, present-day Kaliningrad, Russia. At 35, Goldbach became a professor of mathematics and historian of the Imperial Academy at St. Petersburg. 3 years later, he went to Moscow as tutor to Tsar Peter II, and from 1742 he served as a staff member of the Russian Ministry of Foreign Affairs. During his developing career in the administration of the Academy of Sciences, Goldbach began some work on number theory, much of which in correspondence with Leonhard Euler, most notably, or at least most notably in this case, the Goldbach Conjecture. The original Goldbach Conjecture went as follows. Every integer greater than 2 can be written as the sum of 3 primes. In his time, 1 was accepted as prime, however it is now considered that a natural number greater than 1 that is only divisible by itself in 1 is considered prime. Euler refined his conjecture, and now the conjecture has 2 statements. Every even integer greater than or equal to 4 is the sum of 2 primes, and every odd integer greater than or equal to 7 is the sum of 3 primes. Goldbach's original statement is considered the weak conjecture, whilst Euler's refinement is the strong conjecture. Some simple examples of the even statement of the conjecture may be 4, represented by 2 plus 2, 6, represented by 3 plus 3, 8, represented by 5 plus 3, and so on. For the odd conjecture, there is 7 written as the sum of 2, 2, and 3, 9 written as the sum of 3, 3, and 3, 11 written as the sum of 2, 2, and 7, and so on. The general forms of the 2 statements of the original conjecture are thus. For the even statement, 2n equals p plus q, where n is greater than or equal to 2, and p and q are prime. For the odd conjecture, 2n plus 1 is equal to the sum of p, q, and t, where n is greater than or equal to 3, and p, q, and t are prime. Having a uniform equation will make the mathematical manipulation for the subtraction alternative much more straightforward. But before that point, some properties and bounds of the original conjecture will have to be explained to help find new properties and bounds of the subtraction alternative. For the original even statement, a notable phenomenon occurs when a prime integer used as part of the sum is 2. 2 is the only even prime integer. All other even integers are divisible by 2, i.e., not prime. This means that all other prime integers are odd. In the general form, p plus q can be written in only 3 ways. Only 3 ways, as the commutative property of addition allows that the sum of p and q can also be written as the sum of q and p. Even plus even is even plus odd is odd, and odd plus odd is even. Thus, it can be said that if one of the primes in the sum used to represent an even integer is even, then both primes used in the sum must be even. If it's even, then it's 2. Thus, the unique combination arises for 4 written as the sum of 2 and 2. And, since 2 is the least prime integer, and if 1 prime is 2, then both must be 2, that makes 4 the least positive even integer to be considered for this conjecture. Negatives are not considered, as that suggests that either the primes used are negative, and they cannot be, or there is the use of subtraction, of which there cannot be either. No upper limit on the even conjecture has yet been found, so the accepted bounds thus far remain to be greater than or equal to 4 for the even statement of the original Goldbach conjecture. For the original odd statement, there is another interesting case of the use of 2 as one of the primes in the summation. In the general form, p, q, and t can be written in the following ways. Odd plus odd plus odd is odd. Even plus odd is odd. Even plus odd is even. And even plus even is even. Therefore, if one of p, q, or t is 2, exactly 2 of p, q, or t is 2. The bounds for the odd statement also rely on the special case of 2, as 2 is the smallest prime number and the maximum times 2 can be used is twice. The next largest prime integer is 3, and the sum of all 3 primes is 7. Though a tough sentence to say, demonstratively, it should be straightforward. Moreover, negative odd integers are not considered for the same reason as in the original even statement, as that suggests that either the primes used are negative, and they cannot be, or there is the use of subtraction, of which there is not. A quick note on modern progress. In 1938, Theodor Esterman proved that almost all even numbers are the sums of 2 primes. Most recently, the conjecture has been verified up to 4 quintillion by electronic computational means. However, at most, the weak conjecture, that being every integer greater than 2 can be written as the sum of 3 primes, was proved by Harold Helfgott in 2014. For the subtraction alternative, there has been development by Chen Jingrun, who strengthened it to be every even integer can be expressed as the difference of an infinite pair of consecutive primes. In researching Chen, this is a quick side note, he was a Chinese mathematician who made a significant development in the area of analytic number theory. A quote from the National Center for Biotechnology Information states, "On the verge of solving Goldbachs Conjecture in 1984, Chen was struck by a bicyclist while also bicycling and suffered severe brain trauma. This human being was truly amazing." To further quote, although he died in 1996 at the age of 63 after surviving brutal political repression, being deprived of neurological function at the very peak of his genius, and having to be supported by his wife, Chen ironically became a symbol of dedication, perseverance, and motivation to his students and associates, to Chinese youth, to a nation, and to mathematicians and scientists worldwide. But back on track. Having gone over the history of Goldbach and the properties and bounds of his conjecture, we can start to really look at the subtraction application. There will be 3 cases, 1 even case and 2 odd cases. The even case will consider this equation, where 2n is written as the difference of p and q, where any even integer can be represented as the difference of 2 primes. The first odd case will be considered as 2n plus 1, represented as the difference of p, q, and t, and the second odd case will be considered as 2n plus 1, represented as the difference of p and q plus t. For both odd cases, the bounds allow for all odd integers to be considered. Another notation for the second odd case may be 2n plus 1 written as the sum of p and q subtract t. The reason that only the first notation will be considered is that the 2 generalizations are fundamentally the same. Rearranging either produces the form of the other, causing only a change in the notation of the resulting properties. Therefore, to keep it simple, only the first notation will be used. And the number of pairs, or triplets, of primes used to produce the even, or odd, integers selected via subtraction will not be expanded on, as the intention here is to simply demonstrate that it is as plausible as the original conjecture. And now, to the subtraction alternative. The first case, the even case, as stated, the even case will consider the equation 2n written as the difference of p and q, where any even integer can be represented as the difference of 2 primes. Examples may include 10 written as 23 minus 13, 0 as 31 minus 31, negative 2 as 11 minus 13, and negative 44 as 17 minus 61. In this case, P and Q have the same property of being even as in the original conjecture. If P equals Q equals 2, then by the general form the even integer specified would have to have been 0. However, if the even integer selected is 0, then the only restriction is that P and Q must be equal, and by the additive identity, this suggests that 2 does not necessarily have to be used. If it is not used, then this specific instance of 0 being the selected even integer, then 2 will never be used. For the bounds of the even case, 3 things must be considered: the case of 0, the least positive even integer, and the greatest negative even integer. The case of 0 is taken care of, leaving the cases of the least positive even integer and the greatest negative even integer. Keeping in mind, the defining of the original conjecture's bounds specified only a lower bound, and that may be enough to allow the even case alternative to have the same assumption of an upper bound of its positive even integers as it did in the original even conjecture. That being said, the least positive even integer is 2. By sheer example, 2 can be shown to be in the bounds, and with the assumption of no upper bound, it may be assumed that all even integers greater than or equal to 2 are members of the bounds of the even case alternative. The other consideration is the greatest negative even integer, and that is negative 2. Negative 2 can be obtained by altering the order of the primes used in the example of 2. This in turn implies that all negative even integers can be shown to be in the bounds of the even case alternative. Thus, taking the union of all the individual bounds shows that any even integer may be considered for the even alternative conjecture. Furthermore, it can be inferred from the general form that in order to obtain a positive even integer, P must be greater than Q, and to obtain a negative even integer, P must be less than Q. Next, the first odd case alternative. It will be considered as 2n plus 1 represented as the difference of P, Q, and T, where all odd integers may be considered to be written as the difference of P, Q, and T. Examples of this alternative are 11 written as 19 minus 5 minus 3, 1 as 13 minus 7 minus 5, negative 1 as 3 minus 2 minus 2, and negative 45 as 5 minus 13 minus 37. For the cases of P, Q, and T being 2, the table demonstrates that, just like the original conjecture, if one of P, Q, or T is 2, then exactly 2 of the primes used are 2. There is a specific case, as highlighted, where the two 2's cancel one another out. This then shows that the odd integer picked is itself a prime integer, and thus these two cases are low-hanging fruit for finding the 3 primes whose difference make the odd integer. Other properties as to what P, Q, and T begin to appear with the first odd case alternative. Applying the distributive property, the first odd case alternative can be shown as 2n plus 1 set equal to P minus the sum of Q and T. Then, 2 properties can be inferred. If the odd integer selected is positive, then P must be greater than Q plus T, and if the odd integer selected is negative, then P must be less than Q plus T. And since 0 is not odd, it does not play a part. Thus, every odd integer is either positive or negative, and is achievable by the first odd case alternative's operations. In addition, if P is even, Q plus T must be odd, or, if P is odd, Q plus T must be even. The bounds for this case may be derived by that of the original conjectures. The least positive odd integer was 7, with an open assumption on the upper bound. Through examples, each odd integer less than 7 can be shown to be in the bounds as well. For negative numbers, we take the difference where P is greater than Qt, giving the same magnitude of the odd integer as P less than Q plus T, but by definition, the odd integer will have opposite signs. Because of this, and the fact that all positive odd integers are shown to be in the bounds, all negative odd integers can be considered in the bounds, and therefore all odd integers can be considered in the bounds of the first odd case alternative conjecture. Lastly, the second odd case alternative. It will be considered as 2n plus 1, represented as the difference of p, q, and the addition of t, where all odd integers may be written as the combined of these operations. Examples of this alternative are 1 written as 11 minus 13 plus 3, negative 9 as 2 minus 13 plus 2, 3 as 3 minus 3 plus 3, and negative 15 as 31 minus 53 plus 7. For the cases of p, q, and t being 2, the table demonstrates that, again, just like the original conjecture, if one of p, q, or t is 2, then exactly 2 of the primes used are 2. There's a specific case, as highlighted, where the two 2's cancel one another out. This then shows that the odd integer picked is itself a prime integer, and again, low-hanging fruit. The bounds of the second odd case alternative are also straightforward as in the first odd case alternative. Allowing the original odd conjecture's smallest positive odd integer, 7, the positive odd integers less than 7 can be shown by example to be in the bound. Then, by taking the difference where p plus t is greater than q results in the same magnitude of the odd integers as p plus t is less than q, where, by definition, make the two opposite signs. Thus, altogether, it can be shown that any odd integer can be considered when using the second odd case alternative. As a result, the subtraction alternative may be considered a standing conjecture with its own properties and bounds. The subtraction alternative can be stated in 3 cases, 1 even case and 2 odd cases. For the even case alternative, n is any integer and p and q are prime. For the first odd case alternative, n is any integer and p, q, and t are prime, as is true for the second odd case alternative, where n is any integer and p, q, and t are also prime. Overall, it would appear that Goldbach's conjecture and its subtraction alternative have quite a few things in common. The properties of each of the alternative cases align with the properties of the original statements. However, the notable difference between the two is the extended boundaries. Negative integers may be selected, along with 0, and the few positive integers not already included in the original conjecture's boundaries are included in the subtraction alternative conjecture's boundaries. Thus, they seem to be, indeed, sister conjectures. This presentation is made for the review of the Mathematical Department of Arkansas Tech University as a senior undergraduate capstone project. In the making of this and in the writing of the thesis itself, I used the work from Eric Weinstein in Math World from Wolfram.com, T. Nagel in the Introduction to Number Theory, and work from J.J. O'Connor and E.F. Robertson in Christian Goldbach, School of Mathematics and Statistics. Links to online sources and photos used in the thesis and presentation are offered in the description. Thank you for watching, and stay safe, stay healthy, and God bless.